Hello, everyone. Today we're going to go over section 4.3 over standard deviation. The tools that we have used to summarize distributions of data so far are very stable against changes in outlier data. This certainly has its advantages. There are certainly situations where one score significantly larger or smaller than the majority can give a misleading impression of a distribution. On the other hand, the extremes of a distribution can at times be important to consider. In this section, we turn to the mean and the standard deviation. These two related statistical measures give a better picture of a distribution where the outlier data is more important. First, we'll talk about the arithmetic mean. The arithmetic mean, often simply called the mean of a distribution, is probably the measure of central tendency with which you are most familiar. This is, for example, the average that is usually used for calculating your overall grade in a course. To calculate the mean, add all of the values in the distribution, then divide by the number of values. For a distribution of scores labeled as x values, we denote the mean as x bar, x with a bar over it, and write the formula for this calculation as x bar equals sigma x over capital N. The sigma, or sum operation, tells us to add together a string of numbers. So sigma x means add together all of the x values. In other words, x bar, the mean, is the sum of all the x's divided by how many there are. For example, in a small distribution with scores 1, 2, 3, 6, and 8, we would calculate the sum of x to be 1 plus 2 plus 3 plus 6 plus 8, which is 20. And so x bar, which is the sum of the x over how many there are, would be 20 over 5, since there's 1, 2, 3, 4, 5 scores, and 20 divided by 5 is 4. As we saw with the median, there are some tricks that we can use to find the mean when a distribution is presented in a frequency table. We turn once again to the survey of shoppers at a local mall as an example. So shoppers at a local mall were polled to find out how many stores they planned to visit during their trip. The results are shown in the table below. Now, find the mean of this distribution. Understand the problem. We have a frequency table of data and want to calculate the mean. Devise a plan. To find the mean, add all of the scores together, then divide by the number of scores. Sorry, I said stores, I meant scores. The frequency table emphasizes that we will add the same score several times in the process of doing so. We remember that multiplication is a shorthand for repeated addition, so we can quickly find the subtotal for each row of the frequency table, drastically cutting down our computation time. In other words, instead of adding 1 plus 1 plus 1 3 times, plus 2 plus 2 plus 2 plus 2 plus 2 5 times, plus 3 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 7 times, and so on and so forth, we can just multiply. 1 times 3 is 3. 2 times 5 is 10. 3 times 7 is 21. So let's carry out the plan. Once again, we need to start by calculating the total number of scores in the distribution. So adding together the frequencies, 3 plus 5 plus 7 plus 8 plus 11 plus 18 plus 12 plus 9 gives us 73 total responses. We introduce a new column in the frequency table, the subtotal for that row. So that's the multiplication column. 1 times 3 is 3. 2 times 5 is 10. 3 times 7 is 21. 4 times 8 is 32. 5 times 11 is 55. 6 times 18 is 108. 7 times 12 is 84. 8 times 9 is 72. Now, we can add together all of the subtotals, 3 plus 8 plus 21 plus 32 plus 55 plus 108 plus 84 plus 72 to get 385 as the sum of our x's. Again, if we didn't do it this way, we would have to add 3 1s and 5 2s and 7 3s and 8 4s and 11 5s and 18 6s and 12 7s and 9 8s. It's a lot easier to do the multiplication first and just add up 8 numbers than it is to add up 73 numbers. Once we have how many there were, which was 73, and once we have the sum of the x's, which was 385, we can calculate the mean x bar as the sum of x's over n, which is 385 divided by 73, which is about 5.27. So the mean of the distribution is 5.27. The standard deviation is a measurement of how close the scores in a distribution are on average to the center of the distribution. The figure below shows two normal distributions with the same mean, x equals 0, x bar equals 0, excuse me, but different standard deviations. The solid distribution has a standard deviation s equals 2, and you can see that the scores are more spread out. The dotted distribution has a standard deviation s equals 1, and you can see that it has more scores close to the center instead of being spread out like the solid distribution. The calculation of standard deviation involves performing several operations on every score in a distribution. Let's consider a small distribution with 4 data points, 3, 5, 7, 9. Before finding the standard deviation, we need to know the mean of the distribution. So we find x bar, add up our x's, 3, 5, 7, 9, divide by how many there are, 1, 2, 3, 4, and we get 6. Now, to calculate the standard deviation, we set up a table which has each score in its own row. So a row for 3, a row for 5, a row for 7, a row for 9. You can already see how this is going to get messier the more scores we have. This is only 4 scores. In the second column, we calculate the deviation from the mean for each score, and that would be the difference between that data point and the mean of the distribution. So we take our x and we subtract x bar, the score minus the mean. The mean, remember, was 6. So for 3, we go 3 minus 6 is negative 3. For 5, we go 5 minus 6 is negative 1. For 7, we go 7 minus 6 is positive 1. And for 9, we go 9 minus 6 is positive 3. So first column has our score. Second column has our score minus the mean. If you want to make a column in between that is just x bar so you can see 6, 6, 6, 6 in between these to help you with your subtraction, you are welcome to do so. Next, we square these values to arrive at the squared deviation x minus x bar squared. Remember, no matter if a value is positive or negative, its square is always positive. So you should never see a negative value in the squared deviation column. Square -3 and get 9. Square -1 and get 1. Square 1 and get 1. Square 3 and get 9. The standard deviation is an average on these squared deviations. So similar to the mean, we start by adding them all together. The sum of our squares would be 9 plus 1 plus 1 plus 9, or 20. However, we do not divide by the total number of elements n the way we would to calculate mean. We know that the scores in a sample usually underrepresent extreme data. This would make the standard deviation smaller than it should be. To compensate, we divide by n minus 1 instead. So the formula that we're following so far is going to be the sum of our squared deviations divided by n minus 1. Since our n was 4 with 1, 2, 3, 4 data points, n minus 1 would be 3. So 20 divided by 3 gives us 6.6 repeating, approximately 6.67. We are not done. To finish up, we remember that this value is for the squares of the deviations, so we undo that in a sense by taking the square root. S would be the standard deviation, the square root of 6.67, or about 2.58. So standard deviation is the square root of the sum of our squared variances, our squared deviations, divided by n minus 1. So the square root of all of that. So standard deviation of a sample. It's going to be different for a population. We're going to look at that later. Right now, we're focusing on a sample. The standard deviation of a distribution of data collected by sampling is given by the formula S equals the square root of all the sum of x minus x bar squared divided by n minus 1. How did we find all that? We did a row for each x, and then we subtracted the mean x bar from each of those, and then we squared each of those, and then we took the sum of all of those. Then we divided by n minus 1, and we took the square root. It's a very complicated formula, but as long as we follow the same thing every time, we can arrive at the correct answer. So the data below in example 2 are scores on the first quiz for a geology class. We have 4 rows of 5 data points each. That means we have 20 scores here. 999, 88, 88, 777, 77, 666, 666, 55. We want to find the standard deviation of the distribution. So understand the problem, 20 data points, we need to find the standard deviation. Devise a plan. What do we need for standard deviation? Well, we need to know the mean, and then we have to set up a table that has a row for every single data point. Calculate the deviation from the mean, get the squared deviation, add them together, and use that value in the standard deviation formula. So let's carry out the plan. First, to find X bar, to find the mean, we need to add up all of our data points and divide by how many there are. So with our calculator, we go 9 plus 9 plus 9 plus 8 plus 8 plus 8 plus 8 plus 7 plus 7 plus 7 plus 7 plus 7 plus 6 plus 6 plus 6 plus 6 plus 6 plus 6 plus 5 plus 5. Ooh. We get 140, and then divide by 20 because there's 20 of them. 140 divided by 20 gives us a mean of 7. Then we have to set up a table for calculating standard deviation. We saw how complicated it was when there was only 4 scores. This one has 20 scores. So there's 20 rows, and we list out each X. Then, for the second column, we subtract the mean. We subtract 7. So 9 minus 7 is 2. 9 minus 7 is 2. 9 minus 7 is 2. And then for all the 8s, 8 minus 7 is 1. For all of the 7s, 7 minus 7 is 0. For all of the 6s, 6 minus 7 is negative 1. And for all of the 5s, 5 minus 7 is negative 2. Then we have to square all of those. 2 squared is 4, 1 squared is 1, 0 squared is 0, negative 1 squared is 1, and negative 2 squared is 4. Now that we have all of our squares, we add them up to get the sum of squares. And if we add up 4 plus 4 plus 4 plus 1 plus 1 plus 1 plus 1 plus 0 plus 0 plus 0 plus 0 plus 0 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 4 plus 4, we get 30. Plug that into the formula. The sum of the squares we just found was 30. N minus 1 would be 20 data points minus 1 would be 19. 30 divided by 19 and then take the square root gives us approximately 1.257. So the standard deviation is 1.257. Example 2, another way. Notice in the last example that each score in the distribution repeated several times. We could have written this data as a frequency distribution. So there were 3 9s, there were 4 8s, there were 5 7s, there were 6 6s, there were 2 5s. Then we could have just done subtracting the mean for each of the data points. So 9 minus 7 is 2, 8 minus 7 is 1, 7 minus 7 is 0, 6 minus 7 is negative 1, 5 minus 7 is negative 2. Find each of the squares. 2 squared is 4, 1 squared is 1, 0 squared is 0, negative 1 squared is 1, negative 2 squared is 4. And then multiply each of our squares by how many of them there were. 4 times the frequency of 3 gives us 12. 1 times 4 is 4. 0 times 5 is 0. 1 times 6 is 6. 4 times 2 is 8. So this way, we only needed to calculate the squared deviation once for each unique value in the data set. And we would find that our n, how many there were, would be the sum of the frequencies. The sum of the squares would be the sum of our subtotal column. 12 plus 4 plus 0 plus 6 plus 8, which gives us 30. And then we have our 30 for the top, our 20 minus 1, 19 on the bottom, the square root of 30 divided by 19, again, 1.257. So that's a bit of a shortcut, but I honestly do not recommend doing the shortcut because there's too much room for error. I honestly, even though there were 20 rows, recommend doing it with 20 rows. But there are going to be problems presented in frequency style that we do have to do it this way. When we built up the standard deviation formula, we divided by n minus 1 instead of n because we were worried that random sampling would underrepresent extreme data. This would not be a concern if we looked at data on an entire population. Data on the population means information on literally everything that fits the category you are studying. Say we want to make a prediction about the heights of students at a local college. Population data means that we would analyze the height of every single student at the college. On the other hand, a sample is a smaller group, which is assumed to be representative of the population in some way. Instead of finding the heights of every student, maybe we measure the heights of everyone taking a statistics course this semester and assume that the results for the entire student body would be similar. Data on a population is more difficult to acquire and in many cases is practically impossible. One place we can see the entire population is in a theoretical distribution. Theoretical distributions are based on experiments with known theoretical probabilities. For example, we saw in chapter 2 that if you roll 3 six-sided dice, there are 216 equally likely possible outcomes. If we care about the results after adding the dice together, we get the following frequency table. This is the entire population of possible dice rolls. So a sum of 3 could only happen one time. That's if we roll 1, 1, and 1 and add those together, we get 3. The sum of 4 happens 3 times, the sum of 5 happens 6 times, the sum of 6 happens 10 times, so on and so forth, all the way through the sum of 18 only happening once, and that would be rolling a 6, 6, 6. The mean of a population is calculated exactly the same as the mean of a sample. The only difference is, instead of using x bar, which is for samples, we use the lowercase Greek letter mu, which is this weird looking u. You might also know it from science as the micro symbol, to represent that the mean is from a population and not a sample. So recall our n here was 216. If we add up a subtotal column, so 3 times 1 is 3, 4 times 3 is 12, 5 times 6 is 30. Add those all up, we get 2,268. 2,268 divided by 216 is 10.5. Add them up, divide by how many there are. That is the mean. But instead of x bar, we're using mu because this is a population, all of the possible sums of our dice roll, instead of a sample. The standard deviation also works very similarly. We use a new variable here as well, the lowercase Greek sigma. So capital sigma is that E-looking Greek letter. Lowercase sigma is the O-looking Greek letter. The one difference in the calculation is that we will divide by n instead of n minus 1, since we no longer need to worry about estimates. We can't be undersampling or oversampling when we're not dealing with a sample, when we're dealing with the entire population. So we just divide by n. So recall, our mean, mu, was 10.5. Our n, the number of things we have, if we add up all of the frequencies, is 216. So we make our columns. Now here we are all but forced to use the frequency version of the table. Otherwise, we would have a huge table with 216 rows. There would be a 3, and then 4, 4, 4, and then 5, 5, 5, 5, 5, 5, 6 of those, and then 10 sixes, 15 sevens, 21 eights, 25 nines, 27 tens, 27 elevens, and so forth down the table until we had all 216 rows. We don't want to mess with that. So we'll leave this in frequency. Take each of our individual x's, our individual results, and subtract the mean. 3 minus 10.5 is negative 7.5. 4 minus 10.5 is negative 6.5. 5 minus 10.5 is negative 5.5. 6 minus 10.5 is negative 4.5. 7 minus 10.5 is negative 3.5. And we go on and on and on and on until we get all the way to 18 minus 10.5 is 7.5. Once we have the deviation, once we have the x minus mu, we square that. Negative 7.5 squared is 56.25. Negative 6.5 squared is 42.25. Negative 5.5 squared is 30.25. And we continue down and down and down and down until we get all the way to 7.5 squared is 56.25. Now we need the subtotals. This is just what we had for each individual result. So this is what we would have if we had, for instance, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. But we have 1, 3, 3 4s, 6 5s, 10 6s, 15 7s. So we have to multiply. 56.25 times the frequency of 1 is 56.25. 42.25 times the frequency of 3 is 126.75. 30.25 times the frequency of 6 is 181.5. 20.25 times the frequency of 10 is 202.5, and we keep going with our squared deviation times our frequency equaling our subtotal, all the way to 56.25 times the frequency of 1 is 56.25. The sum of our subtotals is the sum of our squared deviations. So we add up 56.25 plus 126.75 plus 181.5 plus 202.5 all the way to 181.5 plus 126.75 plus 56.25. And that gives us 1,890. So the sum of our squares is 1,890. Our n was 216. If we divide 1,890 by 216, we get 8.75. And then when we take the square root of 8.75, we get 2.958 and some more digits, which rounds to 3.0. Okay, that is the lecture for 4.3. Next time I see you, we're going to go over the homework for 4.3.